Okay, so that's a basketball over there, and it's rocket powered. Okay? So it's a rocket powered basketball. And then this graph over here is as time goes by, it's showing that at every moment it shows the velocity of the basketball as it's heading to Pluto to help it regain its planet status or something. Okay, so questions for your table. What kind of function is V? Rate of change or accumulation? Orders dependent, independent quantities. I just need to see something here fast.
Was V the one on the left or the one on the right?
Well, there's only one. It's the one on the left. That's the only. Okay. Sorry. Going back. Yes. Yes. Okay. What do you think? So yeah, talk for 30 seconds at your table. What kind of function is V? Rate of change or accumulation? Identify dependent and independent variables. Go. I will let you know when you need these. Okay, what do you guys think? What kind of function is V? Rate of change. Okay, do y'all think it's rate of change? Okay, rate of change. Dependent quantity is, or dependent variable is? Velocity, independent? Time. Okay, it's the velocity of the rocket dependent to the time elapsed since launch independent. Okay, how about this? We want to develop the accumulation function associated with V. What are its associated independent and dependent quantities? So what would the dependent quantity be for let's start with independent. We want the accumulation associated with this would be, what would the independent quantity be? Same one, exact same variable, right? Time. And what would the dependent quantity be? Height in meters. Okay, so we'd be trying to find h, height, as a function of time elapsed. Okay, so here's some questions. The third of which being the most critical. Okay, so express the coordinates of the point on the graph when t equals 5. What does the value of V of 5 represent, and what does V of 5 mean for values associated with the accumulation function? So we'll take a minute or two, answer these questions. So, this third question, big idea that we've worked on. Big idea that we've worked on. If you're just kind of saying stuff like, oh, at 5 seconds, the speed is v of 5, this is not a big idea, right? What's the big idea of the meaning of this? What's the big idea? Okay.
Oh, it's when you do the interval thing.
Okay, so the coordinates of the point are? 5 v of 5. This is like an old version of this. Look at this. Okay, and what is v of 5 represents the rate of change of the rocket's height at the moment t equals 5 seconds. Is that right? The rate of change of the rocket's height. Okay. Who thinks they got number 3? All right, so maybe this number, the way I answered number 2, maybe will spark your memory. The way that I answered number 2, maybe it'll spark your memory. And so let's work on number 3 for another minute or two. So what does this mean? That FV5 is the rate of change of the rocket's height. What does that value then mean? Go. So if it's a rate of change, how are we defining rate of change?
Right there. And then after that we do the average rate of change.
A BF5 times the time of interval that we say it's staying constant for, times the change in time. Something like that.
Okay. Given a change in time, what?
The change in height.
The change in height is
V of
5
5
times the change in time. Remember this? Remember this mantra? We spent a day or a week on it, and then we've seen it several times. What is the rate of change? It means given a small change in your independent variable, the change in the dependent variable is that value times the change in that you picked. So
The change. So does it say given a change in the height of the rocket? No. Given a change in time, a change in height of the rocket.
yeah, this is the wrong PowerPoint. I have a different PowerPoint that's updated, so I don't know which one this is. Okay. In other words, what? dH equals V5 dt. But there's kind of a caveat here, a new condition that we need on this. What is that? What interval? Okay, only at 5, that's true, and also? Is it a constant rate of change? Is V5 constant rate of change?
At that moment, yes.
Okay, at that moment, yes. Therefore, for this to work, what has to be true? Yeah, we need a small dt. Right? Near 5. If you don't have that, then this doesn't work, right? If it's not near 5, it certainly doesn't work because away from 5, it's a different rate of change. And once you're near 5, if your interval is, if your dt is too large, then your change in height won't be accurate, right? So because it's a continually changing rate, this only now works for very small changes of t. You can just assume a constant rate for just a small time around 5, and not a larger interval. Does it make sense? Okay. Comments, questions? Okay. Okay, so we want to, and that we did with the oil problem, we said, if we do it by little teeny intervals, it was going to take forever. So we said, all right, let's kind of get an overall picture by using large intervals. All right, so I want you guys to graph intervals on your graph of every 0.9 seconds. All right, so these we're going to call delta t's, not dt's. We're going to call delta t 0.9. And so the question is that a variable or parameter? Delta t. You don't have to whisper. Oh, no, yeah, no, it's just so she said it's a parameter. Yeah, so it's a parameter because in the given situation, it stays, these intervals stay at a width of 0.9. But we could change that, but that would be a new situation, right? And then t is varying through those intervals, right? So t varies through intervals of 0.9. All right, so then I want you, this is for your paper now, so then you're going to first find those values or highlight the points every 0.9 seconds, and then that will help you sketch the approximate rate of change function using the rate at the left side of each interval to define the constant rate for that interval. And then I'm just going to, while you guys are doing that, I'm going to make sure that this PowerPoint is going to go where I want it to go. You got this. You can do on your sheets now. Is the task clear? Can I turn off the screen? So 0.9. Okay.
Did you say the left of the interval?
Yeah. Is that the left? What's that?
Doesn't it go the other way if it's the left side? So like this.
So if it's left, the flags fly out to the left, and if it's right, the flags fly out to the right.
Oh, is that what that means?
No, I'm kind of saying what you're saying. So we want to use the rate at the left side of the interval to be the constant rate for that whole interval. Right? We want to use the rate at the left side of each interval to define the rate for that interval. So is that what this is doing? No, just look at an interval and you say, if I'm using the left, I'm using the rate at the left side of that interval to be the constant rate for the whole interval. So say that interval right there. What's the rate at the left side of that interval? So you want that interval, then yeah, exactly. You want the constant rate. Well, not that. It's just constant rates, right?
Oh, so that.
Yeah. So now that constant rate is the same as the rate at the left.
Versus for this interval, it'd be the right side is here.
Yeah, if you do the right side of it there. That's right. Okay, we good? Okay, so the original rate function, I'll call it r sub h of t, or what we said v of t, is actually t to the 1.3. So we may need that here in a little bit. All right, so what I want to do is I want to find the approximate height of the rocket using this the rate function you just sketched. A of 5 using the same rate function, but with direct calculation, not using A. So I don't want to build the whole thing. I don't want to build this. We've done that before, right? So over here, this function is A of x, and what is the structure of that function? What does it look like? What's that? It's a piecewise function, right? And each piece is. So if you were to talk about what's the structure, so it's piecewise, what's the structure of each piece? Remember what this is? So what would the structure of each piece be then?
It's for each v of like 1 or v of 2, v of 3. Right? Right. The rate at the beginning.
The rate, and then after that, the accumulation? The structure.
The first line would be
I'm talking about any arbitrary line. What's the structure of any arbitrary line in that function?
rate times the change in x plus previous accumulation.
Okay, there you go. Yep. Y final is Y initial, all the previous accumulation, plus the rate times the change in x in the current interval, right? The rate times the change in x in the current interval. Okay. So now I want to find A of 5, not by plugging it into this thing, not by finding this and plugging in 5 and letting the function do the work, but I just want to do a direct calculation. What would it look like? So, yeah, this is 5 right here. What would it look like if we just did one calculation to find A of 5? So what would it look like just to write out one calculation, regardless of what, not building the A function from scratch, but just all I want to do is get, as fast as I can, get A of 5. What would that look like? What would that look like to do that? In other words, this right here, right? So this kind of shows a 5 right there. This the current value is t equals 5, and that would be all the accumulation totaling up to a of 5. What could I do to do that? Yeah, Bill. No, we want to use this approximate rate of change function that you guys just drew. So we want to use the one with the delta t of 0.9. So what would that be like? What would you do? So anything, just your life depends on it, and you've got to find this a of 5 based on r of t that we just found, right? You guys just sketched r of t. Where am I? There I am. This is r, your approximate rate function. How would you get this value a of 5? No, I didn't say that. What I said was without building the whole a function and plugging 5 in. So it's going to use the same principles, but I'm just looking for kind of just a one calculation, rather than does that make sense? So I don't want to build the whole ax function with all this piecewise function. I don't want to do that and plug in 5. Rather, I just want to use the same principles and just find just a of 5. Yeah, Leo. Okay, and how would you get the accumulation at 4.5? So we gotta do everything to get this, right? So how would you get the accumulation at 4.5? No, it's right. But where's a 4.5 going to come from? Right, exactly. How would you get that? So Andrea, so what are we going to do?
You're gonna have to, well, without knowing any specific numbers, you're gonna have to go back and calculate the accumulation at 0.9, and then the accumulation at 1.8,
right,
and so on up
right,
to 4.5,
right,
and sum them together.
Okay, and then after that?
And then you add it to the change of the change in time times the rate at 4.5.
The current rate, yeah.
Yeah, the current rate. To get the accumulation at 5.
Exactly. Okay, so yeah, you guys put it together. That's good. So we need to what? Add up all the accumulation from the completed interval. This is the only way to do it. It's not like, let me try to figure out what he's looking for. No, this is the only way to do it. We got to add up all the accumulation from the completed intervals, right? And then we're gonna have a little bit more in the current interval up to 5, right? Up to t equals 5. All right. So do it. So write down an expression that would do it. You don't have to actually do the calculations. You don't need a calculator here, but let's just write out what would represent the total accumulation from the completed intervals, and then what would represent the accumulation in the current interval, and then we know we're just going to add all those up, right? So go for it. Can you write out what that would be? If you want to just write 2 or 3 and then do dot, 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 that's fine.
So we can just do it times 0.6 this entire time through. 0.9. Yeah, but I didn't do 0.9.
Like factor out 0.9? Is that what you mean?
No, I just realized I was writing in 0.9 minus 0, 2.6.
Right. They're all 0.9. It's a parameter, right? They're all 0.9. No, it's not that bad. All right, so I think most of you got it. So for the completed intervals, we got rate times change in time, rate times change in time, rate times change in time for each interval. And we're going to add up all that accumulation. And then the current interval would be what? What would be the accumulation in the current interval?
Not write it like that.
How did you write it?
I wrote R of 0 times 0.9 of 11.
Yeah, that's fine.
R of 0?
Sure.
But you have V of
Yeah, so I'm just, R of V. Because you define, if this is R,
right.
yeah, then your R of 0 and V will be the same, right? So through the whole interval, through that whole interval, the third interval, every R value will have V of 1.8. And now we're going to actually make it be equal on the left, okay? We're going to actually make it equal on the left because we're not going to build this thing anymore. And I'm going to tell you why in a second. So we're just going to go ahead and call the rate at the left side of the interval the same as the actual rate at the left side of the interval. So yeah, if you put the R's through there, it's the same thing. Okay, and then the current interval, how would we calculate how much we've got so far in the current interval? Brett, did you get that?
Oh, no, I didn't get that one.
Can you do it on the fly?
I don't think so. I'm actually struggling with this a bit.
Where did I lose you?
Huh?
Where did I lose you?
I'm sort of at the first one. I'm still trying to figure out how the first one works.
Yeah, so DH equals rate of change times dt, right? So in order to get A of 5, we're really just summing up lots of little changes in height, right? And each one of those changes is coming from a constant rate. And so we'll do constant rate times the change in t, and that's 0.9 every time. So it's going to be the rate of change in the current interval times 0.9 will give us the little bit of accumulation in that interval, a little bit of accumulated height. And then to get the total accumulated height at 5, we're just going to keep adding up accumulation from the first interval, second interval, third interval, fourth, fifth, and then partial interval. Is it better?
1.3 is part of T1.3, right? It's from T1.3.
T to the 1.3 is just the rate, the original rate function.
Okay.
So if I actually wanted to get a number for this, I would need to then use the T to 1.3. This is the second line. So this is equal. This is all I was asking you to do. And then if we actually wanted to get the value, then we would use the T to the 1.3 to get those constant rates.
Okay, I see it now.
You see it? So now can you go, what would the accumulation be in the current interval?
Oh.
It would probably be. Do we add in completed intervals as well, though?
No, I'm just asking for the accumulation in the current interval.
Okay.
We'd already got the complete intervals. Where's the 11.7 coming from? Just represent it notationally, like we're doing. Like where's the 11.7 coming from?
It's at the blue dot where the current interval ends, and the blue dot meets the line that's coming from the rate of change.
So we want this rate of change, right? We want this rate of change times this amount of change in time. So how do we represent that rate of change?
My paper says something different. I accidentally did the interval wrong. It would be instead 7.8 or something. Around 7, between 7 and 8.
So it's gonna be just like these. It's gonna be v of something, right? So was there? Jesus, did you raise your hand? Oh no, sorry. Go ahead.
Is it V of 4.5 times 0.5?
V of 4.5 times 0.5. So yeah, so it's V of, that's the next one, right? So these are all the completed intervals, V of 0, V of 0.9. Then the next interval would be V of 4.5. So maybe you're estimating 7 or something like that?
Yeah.
Is that what you're doing? Yeah, okay. So, but then we want to represent exactly. Yeah, 7 point something. So representing exactly is the way we did it up here.
Okay.
So it'd be V of 4.5 and then times 0.5. So then our estimate for A of 5 is? The whole thing added up. We're going to add all the accumulation from the completed intervals and then this little more accumulation from the current interval. The V of 4.5 times dt. And so And that's an important note, that these completed intervals, how we chopped it up to start with, that's our delta t, that's our parameter. What about dt? Varying through the interval, right? So this time is going by, at any given time, you have all these past intervals, completed intervals, and then time is increasing, and dt is increasing through the current interval. Yeah, yeah, where is the 0.5 coming from? So if we're at a of 5, we want a of 5. Right, because in this current interval, we haven't completed that interval yet, and we're 0.5 into it. But that actually, so what is dt? So dt is a variable. What does it vary from? From what to what? What does dt vary from? From what to what? She wants 0 to 0.9. Yeah, and then when you get to the next interval, it starts over. It goes 0 to 0.9. The next interval is 0 to 0.9, and then 0 to 0.9. All right, cool. So here's where we're going. So we've already for the oil function, we've done it this way, right? We did it one piece at a time using previous accumulation plus the current change in the current interval, and then we go to the next one and we rewrite up. So why is this? What's the disadvantage to this? What's the disadvantage to doing it this way, like we did with the oil, like you're doing with your GC projects? Problematic about this? Yeah, especially so. What if we make delta t equal to 0.1 or 0.01? We got hundreds or thousands of lines. All right. So what we're currently now doing is we want to write this a function, a5ax. We want to write this a function in one rule, one line, not a bunch of different lines, and it will work no matter what we choose for the size of our delta t intervals. We'll still have just one rule, one line that will generate this function, this piecewise function, as the pieces, linear pieces through each interval. Okay, so that's what we're doing. And that one line has this feel to it. So that's why we're doing this example, because writing the one line version of a of x has this feel of it. We're going to add up all the accumulation to completed intervals, plus however much we've accumulated in the current interval. Yeah, Andrew.
In regards to the one line,
Uh-huh.
does that, if we needed to define certain things, are you expecting that to be somehow part of the one line, or are you not worried about that? So like if I wanted to say delta t is 0.9 and define it in GC as that so that I could use it in there, would that count against me because it would be a second?
Okay, so we got lots of work to do before.
Okay.
So I think once we work through this is going to take some time to work through this. Then I think your question will be answered.
Okay.
Yeah. Yeah. Like I'm not asking you to write it down one line right now.
No, I know.
It's gonna. This is a developmental process because that's hard, right? Ready? Doing something like this in one line. There's some complication to that. There's some sophistication to that, and that we got to build it kind of one thing at a time. Okay, so again, the spirit of the one line function is this, like the example we just did to calculate A5. Totaling like all the accumulation from completed intervals plus accumulation from the current interval. All right, we're back. Okay, so if you remember back toward the beginning, did we look at something like this? And we were identifying parameters and variables. Did we do that? Or was that in the video that I had you watch? Yeah. So that was in the video that I had you watch because that was like the worst day of my life. And so, and I had you watch the video class. Well, in that part of that this was a practice exercise for you to identify what was parameters and what were variables. Well, now we're ready to actually talk about what this thing means. Okay. Now we're ready to. And so this is a little exercise here. Every single question mark is a value that's represented by some variable or parameter. Okay, every single question mark. Double question marks are like an idea, a phrase. Okay, so to to get you started. This gray one here in the lower left. Okay, we haven't actually talked about this. This is the value of x equals a, so I'll turn it on. And a is like our starting point and the independent variable for where we're going to start accumulating. Okay, so where are we going to start accumulating from? From x equals a. Okay, and we'll use that from here on out. But a is where we start accumulating from. So your job is you got 7 more of these to look at and discuss at your table. What does each question mark represent in kind of the context that we're working on here? You got, and again, the double question marks are like you would report a phrase, like it's such and such a function or whatever, and then the single question marks are a value that has some notation to it, some notation, like a variable or a parameter. Okay, so talk through all these. What kind of function? What kind of function? Double red. It's double red. Exact rate of change. Given this is the idea. You know how fast something is changing, right? You know how fast something is changing. That's the double red. Okay? Double black. Our approximate rate of change. We're picking, right, we're gonna create a function that's trying to be like the red one. It's trying to be the red one, but made up of constant rates, right? Trying to be like the red one, but made up of constant rates. And why do we want that? If we have the red one, we have the exact, and why do we want a worse version of it? Right. We need constant rates of change to make progress towards computing accumulation. Okay, let's go with, how about the black single arrow at the bottom? In a letter, the black single arrow in a letter. X, the current value of x. That's just x, right? Because it's from 0, right? So that's just the current value of x. Okay, and then let's do, how about the purple single arrow? Purple single arrow. Which could be also here right now. It could be any of these 3 right now. The single purple question mark. Is it delta x or dx? Delta x. That's representing our fixed interval width, right? Our fixed interval width. And what about the blue one? That's dx, right? It's the change in x in the current interval, right? Change in x in the current interval, which brings us to the gold double. What's the gold double question mark? Current interval. We call that the current interval. And the double purple question mark. Not a sum. Yeah, we call that the completed intervals, right? Completed intervals. All the intervals, completed intervals. Completed intervals. So the last one is the red. We really haven't talked about that yet, but just if you were to explain the red one in words, what would the red one be in words? What is that? Initial, okay, for the current interval. So yeah, it's like the initial value of x in the current interval.
Which one are you talking about?
The red, the single red. It's like the initial x, or we're going to call left x, right? It's the left value, the leftmost x value in the current interval. So whenever you get to a new interval, it changes, right?
So initial x words or left x?
Yeah, we're not, it's going to be actually a function of x. It's going to be left of x, left of x, left of x. But that would work a lot from that. So I'm going to put these all on now. There's x, dx, delta x, completed intervals, current interval, left of x, r of f, and r. So there's everything filled in that we talked about. So again, this is this is the language we need. This is the mathematical language and just the English language that we're going to need when we're trying to develop this one-line accumulation function, which is, like I said, is a complicated thing. But we need to be on the same page in terms of language and variables. Okay, so here we go. Any questions on that? Super important. Alrighty, here we go. So, you know how fast the quantity is changing at every moment? What's that exact rate of change? We want to know how much we have at every moment, which is exact accumulation, right? So here's a snapshot from what we just saw. And we're going to let A be this value just a little greater than 2. And X, the current value of X, be something just a little bit less than 7. But again, our image of this is X increasing through the intervals, right? X increasing through the intervals, but we're just going to pause it and work on the paused situation. So what do we want? We want to know how much do we have, right? What's the accumulation at X equals 6.75? And very generally, how is it we're going to calculate the accumulation at 6.75? What will that just...
Completed intervals plus a portion of the current interval.
Okay, so accumulation from. Yeah. So we're not adding together intervals, but we're adding together accumulation from complete intervals plus accumulation so far in the current interval. Okay, so there's what that looks like, right? So change from completed intervals, and then change from the current interval, right? So the question is, what are these X values for the rates? So what are the X values for those rates? So we're going to have our interval number is going to be J. So J is going to keep track of the interval number. So we've got interval number 1, interval number 2, and interval number 3. So what X values are needed to express the rates for the completed intervals? So basically we're saying what are the... Right here. So let's just go with this. So could you write what those would be? So the picture went away. There we go. So yeah, I'll get the picture in there. All right, so we need, this is R of what? So it's not, we're not sure what it is, right? So it's a little bit greater than 2? 2 point something. So, but we know for sure it's what? A, okay? So then it's up to you to come up with for that second rate is going to be the rate, what? At this X value. That's this one. And then that third one's going to be the rate at this value. And then the current interval is going to be the rate at this value. Again, we want to express these exactly. Express these X values exactly. So can you do it? Can you fill in the blanks there for what X values you'd put in to get the correct rates for the second, third, and current interval? So we could easily just write in delta X for all those. So the second one is? She wants A plus delta X. Sophia likes it. What do you guys think? Kelly likes it. That's it. Okay, in the third interval, what X value do we need to get the rate we want? So what is this? We're talking about this X value right here. It gets us the rate that we want. What should it be? She wants a plus 2 delta x. Agree? Current interval, in this case, x value is a plus 3 delta x. Okay. I went back. So notice, in the first interval, we have a. In the second interval, we have a plus delta x. In the third interval, we have a plus 2 delta x. So the question is, how many in the jth interval? A plus j delta x. Is that right? Look, in the third interval, how many delta x's do we add? 2. In the second interval, we add 1. So we need a, the x value for the jth interval is a plus j minus 1. Everyone see that? Because we need to go across. To get to the third interval, we go across 2 intervals. To get to the 8th interval, we're going to go across 7 intervals. So it's going to always be across 1 less than the current interval, right? Okay, what's the x value for the rate in the current interval? So how many intervals do we go across to get to the current interval? How many intervals is that? Okay, but then what about in any situation? You're really going across what? How many? How does it relate to the completed intervals? How many completed intervals do we go across to get to the current? It's the number of all the completed intervals. So whatever number of completed intervals you have, that's how many delta x's you're going to get to get to the current interval. Okay. What's that? It's still going to be j minus 1 because you're always in the jth interval, and you're going to go across j minus 1. But when we're in the current interval, that number j minus 1 will be all of the completed intervals. It'll be however many completed intervals you have. Does that make sense? Did someone say no? Did someone say no or yes? Okay, we're gonna go. All right, so that the number of completed intervals. So no matter
sum of j, maybe? Is that it?
no, it's still going to be j minus 1. If you consider the current interval to be the jth interval, it's still going to be j minus 1. But if you add
it's just j minus 1 then.
but j is the number of completed intervals. So I guess yes. So it's not j because j is changing. J changes from interval to interval. Right? J is 1, then j is 2, then j is 3. Anyway.
J final?
No, it's the number of completed intervals. That's the answer. Number of completed intervals.